Hello and welcome back. Today we'll be talking about Lagrange multipliers and slack variables. Now, we're still going through the Broyden method for solving a set of functions. So let's say you've got yourself a nice tasty set of functions, right? And you want to find, say, like we've got over here, you want to maximize some function of some variables subject to some other function at a constant. I'll go ahead and redraw that. So we've got, the function here. It's f, and here it's equal to d1, and then we've got a second ring, here's d2, and a third ring, d3. Now, what we know is that d3 is greater than d2 is greater than d1, which means obviously the larger ring, whatever maximum we can get, that will constrain to g of some variables is some constant. The higher of the ring it manages to go through correctly, then the higher that's the maximum. Now, obviously, how do we know which one's correct? Well, for that, gx of y, or g anything of some constant, will be some, we'll go ahead and cut this function, something kind of like, touch correctly, that. Maybe. I don't know. This is just a function. But here, you'll notice here and here, I'll highlight them, here and there, it intersects kind of askew. It just kind of crosses through, nothing special about it. Here, it doesn't even touch this ring, but right there, it is fully perpendicular, fully just touching, which means that would be our maximum. How do we know that? It's easy to look at, and you can easily judge with your human eyes. Ah, yes, that has to be it. Get a machine to draw up as many f of however many variables you have, and you'll eventually, yes, meet that point, but that require a whole bunch. And yeah, you could draw like 3 or 4, see which one's closest, and judge that way, but, well, that's just right back to the problem we're trying to solve in the first place, which is solving a set of equations. Wouldn't it be nice if we had an easy way of perhaps adding in an extra variable so this thing is a little less problematic to solve, a bit less just keep guessing the entire function? Well, for that, we have what's known as a Lagrange multiplier. So, with f, x, y, and g, x, y, these are, of course, two pretty separate functions. But we can combine them into a third function, which we're going to call L, and it will have 3 variables, x, y, and lambda. And that is defined as the function f at x and y minus some multiplier lambda g, x, and y. Well, that's something. And in this case, that lambda is acting as what's known as a slack variable. It is an additional constraint that can be used to help solve an equation. The shorthand here, as shown, is by introducing the slack variable y is greater than 0, the inequality ax is less than b, which may be a bit hard to solve, can be converted to the nice equation ax plus y is less than b, because we know y has to be greater than 0. Which means that ax, which will always be less than b, plus y, which always has to be greater than 0, will equal b. Now we have a third variable and no awkward inequalities. It's all an equality, and we can eventually later on figure out what y would be. And we'll get back to that. That's important. That will be important when we return to our code. We won't do that this part, but it is important, because that can be used to kind of guide a function. Now let's say we've got a function, and we want to make sure the function stays in this box, right? So we've got our function, it's kind of scribbling on here, and we guess the point, here. And, and based upon our whatever code we have set up, it says, I want to go this way. Well, we can't do that. That's outside of our bounds. So it can either, if it's instead, say, going inwards this way, I don't know what this is solving for, but it could be that direction. It won't complain about it. But if it does go this way, it says, well, no, I can't do that. I've run over the boundary. So instead, I wish I had another color. Oh, I do have another color. Instead, it will move up until it can no longer move at that boundary. And in which case, it'd probably actually be moving that way to there, but the point still stands. It acts as a binding variable. A slack variable in this case, which could be used as an inequality when we say you can't go that far out. Whatever you do, it has to be less than this value and greater than that value. We'll call this A, so it doesn't look like another sign. It's hard to say less than A, but it's easy to say something plus some other constant is equal to A. There in our slack variable. Lagrange multiplier helps with that in a way. Lagrange in and of itself is, of course, defined as stuff I'm not super versed with because we're now going into gradients. The short answer is that, you've got some gradients, and what you want is you got two gradients, one for x and y for f, x and y for g. The gradients, the thing you're trying to get is surely somewhere here. I'm pretty sure it's matching gradients. Well, the short answers of gradients becomes x, y, lambda for L, x, y, lambda equal to 0. Meaning at some point that gradient will be none. Meaning the change between the two functions, if I answer that gradient correctly, is none. Meaning they match. They're going the same direction. They are perfectly, not just parallel, they're actually parallel and touching. That's hard to solve when you've got just those two equations of, only f and g, but when you force them into a singular equation by means of this L function, like a lambda, you can now solve both more or less simultaneously. Because, as stated down here, delta lambda, that chunk implies g, that, etc. You can add in more unknowns, but the short answer is by adding in an extra variable into the equation for Lagrange, it means you can solve for that point right there, where they are running perfectly same direction, have the same slope, because obviously you could, again, either go through each iteration of some distance for the function f to try and match some other function g, or by adding in them into one function, you're only solving for one thing. You can then solve the gradient between them, and congrats, which then ties in, of course, back into the whole idea of slack variables, adding an extra variable into a system where you have some weird inequality or constraint. So instead of trying to be like, oh, I'd like ax is less than b, that's hard to figure out, but ax plus y is b is easy to figure out. And we'll be getting to that next time, so that our nice little equation here doesn't go running off into some weird spot if we try and constrain it somewhere. Because right now, it's completely unconstrained. We've cut ourselves a loose cannon function. We don't always like that in math because it might just find some really weird solution. We've got our nice axes here. We've got function A. We've got function B. Well, the smart man says what I'm looking for is obviously at this point here. But if you start at the wrong point, computer might say, oh, well, that point is a solution. Yes, but it doesn't make sense. It's negative and negative. In some systems where you have, say, a distance or a time, that might not be a feasible solution. So you say, well, I want time greater than 0. And if need be, you could also say some other constant greater than 0. Well, again, t greater than 0 is hard to get, but if you have some function x plus some... Oh no, it has written y is 0, x b, y is equal to b. I mean, it has to be greater than that. That means it's less than 0. Plus, we'll just call it y is equal to 0. And y must be less than or equal to 0. Therefore, f of x is equal to t must be greater than 0, which is what we wanted. Therein lies slack variables and an extent Lagrange multipliers. So we'll be constraining our function next time so we don't end up with funny solutions here and instead get the nice solution there that makes physical and sense, or at the very least matches a constraint we've asked.